All right, so we've talked a little bit about uncertainty and using the standard deviation as a way to show us what our deviation from the mean is. So the standard deviation is not really, is not the same as the uncertainty. However, it is typical and you can use the standard deviation as your error, kind of to show the spread. And that's what you do when you report a value. You always report the average value with the appropriate number of significant figures, and then the standard deviation to help people know the spread of your value, okay, from your measurements. Now let's make sure this is an important thing to know. So let's make sure we recognize this. So I measured some volumes of solutions, and this was, I did it four times. And this was the average value for those four measurements, okay? So this is an average with an n value equal to 4. That means an average of 4 different measurements. All right. How many significant digits do I have?
6.
That's right, 6 significant digits. Okay. Now, when I take the standard deviation, I get a value of 0.00238. All right, these are the values that the spreadsheet spits out for me, right? Now let's see, do you remember, we talked about this already, but I'm afraid that some people won't have realized it. Do you remember, how can I report these values now?
What do you mean?
Well, is it appropriate then to write 10.0354 plus or minus, and that's what the standard deviation is, it's a range, 0.00238. Is that a way that I can report this data?
Oh yeah, I think I remember what you're talking about. No, you gotta write the last significant digit is your first unknown, or your first uncertain digit. Is that right?
That's right. So right here, this is the range, really. It's plus or minus 0.002. If this value ranges from plus or minus 0.002, it doesn't matter how much that value or that value range. Does that make sense?
Yeah, because this first one's already uncertain.
That's right. Therefore, again, looking at my third decimal place here, this value doesn't make any sense to report. So what should I report here?
10.03. Oh, and then you have to round so that stays 5.
That's right. So 0.03, you would just round that 5 if necessary, right? 10.035 plus or minus what?
0.00, and then you round that 2.
0.002. All right. So the error is always going to be essentially one value, okay? One digit here. And this digit here these two digits, the last one here and the last one here, should be in the same place. Does that make sense?
Yeah.
So that tells me another additional rule when we're determining significant digits, right? Because how did I determine these significant digits?
Well, you just gave them to us.
Yeah, but I mean, if I had collected data, where did I get all these significant digits?
Oh, the 4 values, I guess you averaged them all together, added them up, divided by 4, and that's how you got the 4 significant digits?
That's right. Each one had 4. I added them together. Sorry, each one had 6, right? 4 decimal points. I added them all together. Therefore, I could maintain all 4 decimal points. Dividing by 4, that's not, you don't have to count that as significant digits. And then my resulting value is limited because of the error of the experiment, all right, or the standard deviation. All right? Good. So make sure we recognize that. Now, what if I have errors on multiple measurements, and I need to combine those measurements and decide what the resulting error is. For example, I measure out 9.92 milliliters plus an additional 9.92 milliliters. And if both of those errors are 0.006 milliliters, right, so the pipette we use, this is our plus or minus on the pipette that we're using there. Does that mean that the error is 19, the sum of these two and the sum of those two?
Probably not, because if you kept adding, you'd pretty quickly get a pretty big error.
That's good observation. If you did this 5 times, your error would go up pretty fast, right? But obviously it wouldn't be no error, right? I don't know why they even would suggest such a silly thing like that. But somewhere in between, I mean, there's obviously still error, and we have to be aware of what kind of error there is. And so what we call this is the propagation of our uncertainty or our error, right? Because if you have uncertainty or range information on multiple measurements, and then you combine those measurements, you need to know a statistically appropriate way to report the error, okay? And the statistically appropriate way, now I want you to recognize that statistics is a science, a field that is not a great fluctuation, but there are degrees of fluctuation. So as people recognize there are better ways to report values or to report range or to express error, right? Then things will change. Things will change. And you can read through papers and see people use different tools to report error. And, there are some more standard ones than others, but there are reasons why it sometimes might be appropriate to use different tools to report ranges. So, as far as propagation of uncertainty, this is pretty standard. I can't say that I've ran into other ways to express propagation of uncertainty. But that being said, it's not always cut and dry. So if I have a value R that I got from measurements A, B, and C, and I combined measurements A, B, and C this way, and this is the resulting R, we want to know what the uncertainty on R is. And the way we do this is if we're adding and subtracting, you take the uncertainty on A. So let's say this was maybe measurement of 10.0378 plus or minus 0.005, right? That 0.005, the plus or minus component here, is my uncertainty. I square it, and then I look at the uncertainty on B, and I square that, and I add it to A. I look at the uncertainty on C, I square that, and I add it to A and B, right? So the sum, doesn't matter if you're adding or subtracting here, the sum of all the squares of the uncertainties, then you take the square root of the whole thing. That will be the resulting uncertainty on R. Okay? So let's look here then. If we dispense 20 mils using a 10 milliliter Class A pipette, and all we have is the uncertainty provided, we don't have our own standard deviation, then take 10 milliliters plus or minus 0.02. I'm adding 2 volumes of these together. My resulting volume is 20 mils. Okay? And when if you use the calibration data, let's see, where did they get the calibration data? Here it is from table 4.28. If you use the calibration data, and again, you can make your own calibration data for your specific tool, then you would use the volume of that calibration data multiplied by or add them together. And for this first set here, if you just said, oh, it's 10 milliliters, I'm going to use 10 milliliters, then you have to use the uncertainty with that comes on the pipette, and the resulting uncertainty would be that 0.02 squared for that 10 milliliters, and then the 0.02 squared again for that 10 milliliters. And then your result would be this 0.028 milliliters as your uncertainty, all right? And you would report that 20 milliliters plus minus 0.03 milliliters. You see how we got that?
Yeah, I think so.
Okay, so that is for delivering the 10 milliliter from our uncalibrated pipette, right, which is completely appropriate. If it's uncalibrated, you just use that as your uncertainty. In the case where you have your pipette and you'd calibrated it, right, and so we're just taking that data from here, but your own calibrated pipette would have a specific value, which sometimes has its own personal error built in, so you might want to, you know, write down on the side of the pipette, I've already calibrated it, this is what its value is going to be every time I deliver it. You add the sum there, but then you get to use, which will be much smaller generally, your standard deviation. And then you get a much smaller, well, in this case, it's only 3 times as smaller, resulting uncertainty. Okay? That makes sense?
Yeah, I think so.
Should we do a practice together?
I think I got it.
Okay. All right. Uncertainty when multiplying or dividing. When you multiply or divide, it's the same thing, except for because you're likely going to be, you could be with different units, right? And so you could be in completely different ranges. Like this could be 0.1 milliliters, and this could be 17.8 grams, right? So they can be completely different units. You're multiplying things together. You can't add things together if they're different units, right? You can only add things together when they're the same unit. But if you multiply or divide, you know, you get other units like grams per milliliter or grams per milliliter per second, right? Gram milliliters per second or whatever it is, right? So you can have lots of different combinations of units. However, these units come in different ranges, right? So you need to take not the absolute error like we do here, but you need to take the relative error. So you need to convert that error to a relative error by taking your error, dividing it by the average or the value for that measurement, right, A, and that gives you now the, not quite the percent error, right, because you didn't multiply it by 100, but it's the relative error. And then you square that and do that same thing for all the errors for all these measurements, add them all together, take the square root of them, and then the resulting value, resulting, let's see, this is supposed to have an equal sign here. The resulting error will be the resulting error divided by this value. So to get it to an absolute value, you'd multiply by R, whatever R is, the number, and then that would give you the absolute value. But generally you don't do that. You just multiply this by 100 and present it as the percent error. Okay? So here you go. Q, I, T, in some electrical current, charge, current, time, all right? Current is 0.15 plus minus 0.1, that's our I. Passes through a circuit for 120 seconds plus minus 1 second. What's the total charge and its uncertainty? Got a 0.15 times 120 giving us 18, so Q equals 18. This uncertainty, 0.01, divided by the 15 there, squared. 1 as the uncertainty here, divided by the 20 squared, add them together, and then that equals our relative uncertainty. All right, the relative uncertainty. If you multiply that by the R here, so this should really be UR over R, right? And then you multiply it by R, equals, what is it, R times 0.00672. This should be UR over R equals 0.00672. And, okay, yeah. So then they bring the R up already. Yeah, so they didn't have the U over R here. Kind of a handful of mistakes so far in this book, but that's all right. All right, so then you have the resulting value of 1.2 if you've multiplied it by R. Is that the absolute error or the relative error? What do you think? 1.2.
You multiplied by the R, so it went back to the absolute error, right?
That's right. Going back to the absolute error. Now, if we had not multiplied the error or the uncertainty here by r, that would be we could call it your fractional uncertainty. And would you want to report that?
I don't know, do you?
I've never seen anybody report that. You'd have to report it as a percent error. So how would you do that?
Oh, multiply it by 100.
That's right. That'd be 6.7%. And a percent error is always easy to understand because if, for example, the resulting value is 18 and I say plus or minus 6.7%, right? That's really clear and everybody knows what to do with that. 18 plus or minus 6.7%. Okay? Very good. And now when you're reporting like this, when you were reporting a percent error, then the way that you decide what percent, how many significant digits your percent should have, is going to be related to how many significant digits you have over here. Okay, so that's a little bit different when you're reporting a percent error. Okay. So uncertainty, or sorry, mixed operations. Anytime we have mixed operations, right, then we have to go to the relative error, right? Relative error. We have to, or we can combine errors. So let's look at this, for example. The relationship between signal and analyte's concentration. We've seen this before here, right? What's the analyte's concentration and its uncertainty if the S total here is 24.37 plus or minus 0.02, SMB is that value, and Ka is that value. Well, we rearrange the equation, solve for Ka, here it is right here, and then we have to subtract these two and then divide. So we can do the subtraction, there it is, the division, so we get our answer, right? But now how do we treat the errors? What do you think?
Well, the top ones, you don't have to do relative error.
That's right. So the top ones, we can just get the errors on these two and get a value there.
But then you got to use that when you divide.
That's right. So you use that error here and you have to make it to the relative error. And notice that we're dividing it by that initial difference right there, the 24.37. You see that?
Yeah.
Okay. And then this 0.003 is the result, or is the value down below. Where is it at? 0.003. Oh, that was Ka. Yeah, wait. Oh, yeah, that's the error on the Ka, right. Okay, very good. So we had to use one rule for addition and subtraction and one rule for division. Okay, very good. All right, so here we have a bunch of equations for propagating error. We introduced the ones for addition and subtraction and multiplication and division, but you have other ones provided as well. We won't be using hardly any of these in class. But again, most of this, or a lot of this material, especially the statistical information that we're going to be introducing, is for reference so that you're aware of where to go. There's so much to spend time on, and we don't have time to get proficient in everything, but we want you to make you aware of many things and get you proficient in things that will be probably most used in graduate school or in medical school. Okay, so and at least give you a foundation for industry. All right, so is calculating the uncertainty important? Why would we do this? Well, usually you would do this when you want to see how effective your method is, right? In the very end of your method, you can calculate the error associated with it. If it's a very large error, then it's not going to be helpful, right? And so as you improve your method, you should be able to constantly calculate the error and see if that's improving. All right?
What value is a good error? Or what value are you looking for?
Well, 5% is a general kind of standard. If you're at 5%, things are good. If you're better than 5%, things are very good. If you're worse than 5%, things aren't necessarily bad, But if you're reaching 10%, then that is generally not a good range to be in. Okay. Good. Excellent. So now moving on to our distribution of measurements. We talked about measuring pennies previously, right? Talked a little bit about measuring pennies. And if you had 7 measurements and got an average here and a standard deviation, and then in a second experiment where you had only 5 pennies measured and got a different average and a different standard deviation, right? What we really want to know is, did I get lucky on this 5 here? Or was there something wrong with this 7? Or how many of these measurements do I have to actually make to get an answer which I'm confident in? And how do you express confidence? How do you know how confident you are? When I was a kid, I used to say things like, I saw that bike for sale over there. I would just say, for sure, this is what is the truth, right? Not kind of realizing that sometimes you just don't see things the way that they are, right? And so as you grow up, you begin to make statements and improve the way you communicate by saying things like, I think it was over there, but I'm not sure. If I were you, I would try to go over there and check it out because I think it's worth it, right? And then when those types of statements become critical for whatever reason, even if it's in a lab setting, you want to begin to say, I'm 93% confident. I'm 99%. You never want to say 100%, right? Because you always have to recognize that you could be wrong. But your communication becomes more effective when you utilize these kind of indications of limit, okay, of the range. So a population is a representation of all the values that exist out there. So every single penny that is in circulation would be our population. A sample of the population, right, is a limited subset, just a limited subset. And we want to know, or have at least statistical ways, or at least be familiar with the standards for the statistical methods of expressing the likelihood of your sample representing the whole population. Have you ever bought light bulbs?
Yeah, I buy light bulbs every once in a while, I guess.
Have you noticed how light bulbs are saying, when I was a kid, light bulbs didn't have much of a guarantee in terms of how long they would last. They wouldn't say that because they just didn't have that degree of confidence. But as I got older, I noticed that light bulbs, or maybe it didn't, I didn't recognize it. But as I got older, I noticed that light bulbs began to say things like, this light bulb will last 5 years or 10 years or 13 years. And I don't think I've ever lived in one place for 13 years, but I'm always constantly changing light bulbs, right? Not every month or anything like that, but every, couple months, the light bulb needs to be changed. It's an interesting thing because it makes you really wonder how these statistics are made. And I'm not too confident that what they're expressing is true, or even statistically honest. It's true that we can make lots of predictions about statistics and or make lots of statistical predictions that are fine statements that are not incorrect statements. But that doesn't mean that they're necessarily appropriate or ethical. They could be misleading. So, to answer any kind of questions we have about the relationship between a sample and the population, or maybe just a single individual within the population, we look at probability distributions. All right. A binomial distribution, an example of a probability distribution, describes a population in which the result is the number of times a particular measurement or a particular value will be found within the population, right? And that's data from your sample. So, for example, now we're not going to look into any of these equations here, but the example here is if I have, I don't particularly like this example. It's the number of carbon-13 atoms in cholesterol. But if we thought about these as the number, just how many times you're going to get maybe the size of a particle, right? So when I was in graduate school, we would measure sizes of our nanoparticles that we were making because they were always a distribution. You would never get perfectly ideal or exactly the same particle size, right? Just a few hundreds extra atoms and you would change the size of your particle. But a tight distribution showed very tight control on your ability to make different particle sizes. And you would count, so usually this would be probability, this would be the number of the particles that had these different sizes. And if you divided them all by the number of measurements you made, you could get a percentage, and then you could change it into a probability or out of 1, right? And so you would get these distribution plots. Now, a normal distribution, and we're not going to kind of look at these too much, these equations, but a normal distribution for any measurement that you make on a large population will have this sort of a shape, Now, it depends on what you're measuring, and it depends on the size of your axis here. I could tighten this axis up, and this population would look like this population. This one would get taller here, but I could get this one to have the same shape if I tightened it up, okay? And in a normal population distribution like this, right? So let's kind of give some examples here. Can you think of something that you would measure a lot of and find out or get a distribution like this? I mean, almost anything would fit.
Would the height of a person fit?
That's very good. That's a good example. This would be the average height of a person, and we know that there's a distribution right or left, right? Now, you would want to make sure you said something like the height of a person at the age of 18 or between 18 and 30, right? Because people start off really tiny, right? And they grow.
Yeah, okay.
So you would get a distribution like this if you were trying to measure the lifetime of a light bulb, right? The number of light bulbs that would have a certain length, lifetime, right? It wouldn't be 0 as this is here, but this is just showing the distance away from the average. So again, the average is right in the middle, and a standard deviation for a distribution curve should, if you go to the right and to the left, one standard deviation, and that's what we say when we say plus or minus, right? So let me bring back that paper where we were talking about. If I can find it here. Our average and our standard deviation, which ultimately were expressed like this. Here's our average and our standard deviation, right? This average and standard deviation, that standard deviation should encompass, based on the average and the standard deviation, it should encompass what we 66%, 68% there, 68% of all of the values within that population. All right. So one standard deviation, and that's a plus or minus again, should contain 68% of all the values in a population. If I take two standard deviations, right, then that should encompass, so here's our average value, one standard deviation, two standard deviations away, right, should encompass 95% of all the values within that population. All right. So this is some powerful information in terms of knowing what percentage of all the values within a population contain given increments in standard deviations. Okay, good. So what if we want to do this? Now let's look at this. Let's see, where is this equation at, right? Is that the first time the equation's introduced to us? I feel like it was up here a little higher. That's the first time right there. So if we want to, how do we use this standard deviation information? Well, let's say the amount of aspirin in a pain-killing tablet, that's what analgesic means. It's a popular word in biochemistry and in pharmaceuticals. So analgesic, painkiller. The amount of aspirin in a pain-killing tablet is on average, that's our mu, average, 250 milligrams. Do you remember what this thing is?
That's the sigma, right?
Sigma S for standard deviation, right, is 5 in a random sample of tablets from the production line. And we want to know what percentage of tablets are expected to contain between 243 and 262 milligrams of aspirin. All right. Well, what you can do is you can calculate what we call the deviation, Z, not the standard deviation, but just the deviation of each limit from the average, all right, by taking the 243 to start off with, minus the 250, the average, divided by 5. That's our lower, and then we can do our upper average, 262 minus 250 divided by 5. And these Z values, we have a table here. So we go to this table, and in this table we can see down here, looking at the values for a single-sided normal distribution here, looking at our first column here, we can say, what were our values again?
Oh, I can't remember.
Okay, let's see where we're at. 2.4 and 1.4. So we look at our values, 2.4 and 1.4, and we say that at 1.4, we're 0.08 or 8.08%. All right, we're at 8.08%. Let's write that down here. We can use that later. And then the 2.4 is 0.82%. So this is the percentage. That was the lower limit, right? So this is the percentage, 8.08, that are below 243, and this is the percentage, 0.82, that are above 262. So then if we just take our 100 and subtract the amount below and subtract the amount above, what's left is the percentage that should be within the range of 243 to 262. Does that make sense?
Yeah, I think so.
Good. All right. So, do you want to try to do this one by yourself?
Okay. So 240 milligrams to 250, huh?
Yeah, that's right. We want to know what percentage are between 240 milligrams to 250 milligrams. What percentage of all the tablets we make we would expect to be there.
So you take the 250 minus, or the 240 minus the 250.
Very good. 240 minus the 250. Here's that there.
Yeah, and then divide by the standard deviation, which is 5.
Very good. And that 2 value then, what do we do with that?
That's your Z value. You go look at that on the table.
That's right. Very good. So, let's do our other one. What's the other one going to be?
The other one is 245 minus 250.
Very good. 245 minus 250.
Divided by the 5.
And what's that?
That's just 1.
Good. So Z equals 1 for the 245, the upper limit, and Z equals 2 for the lower limit. All right. So now we'll head to our table here. 1 and 2 are our values that we're looking for. So what does that mean?
So 15.87%.
15.87%.
And 2.28%.
Okay, so what are those values?
Let's see. Which one was the upper?
The Z equals 1 was the upper.
So that means that 15.87% are above 245, and the 2.28% are below the 240.
Okay, very good. So what do we do with these values?
Subtract them both from 100.
That's right. So 100 minus those values, 100% minus those values, will give us the resulting amount or percentage of tablets that we expect to be within the range of 240 to 245, or 13.59%. Now, if you're a quality control and you're trying to determine how many tablets you should measure, how is that going to help you?
Well, if you measure 100 out of all the tablets, then just a little over 13 should have that range.
Very good. That's right. So that's based on the normal distribution. So if you're making your measurements and you see that there's 20% that have that out of 100, then what do?
Well, you got a problem.
That's right. Something statistically is wrong with your setup, your method, right, or your tablet creating process. All right. So confidence intervals for populations. A confidence interval is a way to express how confident we are that our results are within the actual population range. Okay, so mu, again, being our average, and if we have, what we're looking for here is our average with a plus or minus value. So we take our plus or minus value as z, where z here is our distribution, our deviation, times our standard deviation. Okay, so z is how confident we are in assessing this range, and values reported in this fashion are called confidence intervals. So here's a table of confidence intervals. When we want to say we are 99.95% confidence, our z value has to be 3.5. If we want to say we're at 95% confidence, which is usually where we express our confidence, our z value is 1.96, right? Because if our z value was 2, right, what are those called again?
Standard deviations?
Yeah, 2 standard deviations is 95.44. All right, so taking your average and then using a plus or minus of the standard deviation would tell you that it contains 68.26, but plus or minus 2 standard deviations would put you at 95.44%. And if you want to be right at 95%, then it contains 1.96 standard deviations. So to say that your value, so if I make I have a number here where I say the resulting value that I got for my measurements was 10.033 plus or minus 0.004. All right, so I got my standard deviation. So from that statement, if this is my standard deviation, right, here's my average, here's my plus or minus my standard deviation, right? And so how confident are you that all the measurements that exist in the population will be encompassed by this statement?
Are you asking me?
Yeah, how confident are you that all of these, all the measurements that you make will represent the population? Or sorry, all the measurements in the population will be encompassed by this statement?
One standard deviation?
That's right, that's one standard deviation.
So that's 68 point, what is it? Oh yeah, 26%?
Very good, 68.26%. If I wanted to say I'm 95% confident, then instead of expressing one standard deviation, what do I need to do?
95? Can you scroll that down a little bit? That's 1.96 times that.
Right. So if I go to essentially double that, then I'll be 95%, 95.44% to be exact, confident that all the measurements we make will be encompassed within that standard deviation, or that statement. Okay, very good. So what is the 95% confidence interval for the amount of aspirin in a single analgesic tablet drawn from a population of 250 with a plus or minus 5? All right. 95%, that's again almost a 2, 1.96%. So we just take our 250 and plus or minus, and then the 196 times the 5. Okay, or 1.96 times the 5. Good. A population standard deviation from the amount of aspirin in a batch of analgesic tablets is known to be 7 milligrams of aspirin. All right. So a population standard deviation is 7 amongst this batch, 7 milligrams. If you randomly selected and analyze a single tablet and find that it contains 245 milligrams of aspirin, what is the 95% confidence interval for the population's mean? So, the 95% confidence interval for the population mean is our tablet, 245, plus or minus our 1.96 times our 7. All right, therefore, based on this one sample, we estimate that 95% that there is a 95% probability that the population mean lies within the range stated here. Okay, so let's go over that one again. The standard deviation is 7 for a group. That means that 68% of all the values range with a plus or minus 7 milligrams of aspirin. So if you randomly select and analyze a single tablet and it contains 245 milligrams of aspirin, what's the 95% confidence interval for the population's mean? You can just take that single measurement there. If you know that the standard deviation for the population is 7, you can take that single measurement, multiply or use the 7 as its standard deviation, right? Because somebody already measured it lots and lots of times and they found that they have a deviation of 7. So when you take a single measurement and give it the standard deviation and then multiply it by your z-value of 1.96, right? Now we can say that based on this one sample, this suggests that there is a 95% probability that the whole population's mean is within the range of 231 to 259. So you see how that's kind of powerful?
Yeah, that's well, I guess you can do that because somebody measured a lot of tablets at one point, right, and got that standard deviation.
That's right. That's right. So a single measurement can be made, and you can expect or estimate 95% of your tablets to be within a certain range. Okay. Now this isn't normal. That's not normal to take a single sample and express the standard deviation, or the deviation, or the range, express range from that single sample. Usually what we do is we collect n samples from a population that has a known standard deviation and report to the average. And then the standard deviation of the mean, which is known as the standard error of the mean, right? So again, the standard deviation of the mean, right? That's what our standard deviation of the mean is the standard error for the mean. And so the standard error for the mean is different than the standard deviation of the mean. Okay, a statistical nuance, but we want to recognize that when somebody says, my value I got was 10.03 plus or minus 0.02, right? And with a standard deviation of plus or minus 0.02. That is different than the standard error of the mean. Something called the standard error of the mean is the standard deviation divided by the square root of n. Now, have you gathered what n is? Do you know what n is?
N was the number of measurements made in that population, or in that to make that average.
That's right, to make that average. So the standard error of the average will be the standard deviation divided by the square root of n. So the confidence interval for a population's mean is then the average plus or minus z times the standard deviation over the square root of n. Okay, so what does that mean? What is 95% confidence interval for analgesic tablets? If the analysis of 5 tablets gives a mean of 245, we take our 245, we plus or minus the standard deviation here, right, from this example in 4.44. So up here we had a standard deviation of 7. And then 245 plus or minus the standard deviation times 1.96 gives us the 95% confidence interval. And then plus or minus or over the square root of 5 milligrams gives us 4.5 milligrams with a plus or minus 6 milligrams. All right. Now see how without that average of 5 values here, without taking the average of 5, if we would have just taken one value, then this would be 1 down here basically. We wouldn't put anything down here. But if you do it more than once, then you increase the value down here, and that allows this value, which was at 7 before, or actually 7 times 1.96, to go down. Okay? So, let's compare these once again. If you don't take more than one sample, if you just take one sample, your 95% confidence interval for that single sample is that value times the standard deviation times, or sorry, plus or minus the standard deviation times 1.96. If you take more than one sample, it's the same thing, standard deviation times 1.96, but then you get to divide it by the square root of the number of measurements that you make. All right? So that's good. That's good because when you make multiple measurements, the greater this denominator is, the smaller that standard deviation is, or the smaller your confidence interval. All right, so overall statement, we estimate a 95% probability that the population's mean is between those ranges, or 245 plus or minus 6 milligrams. All right. Here we go. An analysis of 7 aspirin tablets from a population known to have a standard deviation of 5 gives the following results. What's our 95% confidence interval for the population expected mean? Go, Fred.
Oh, okay. Let's see. So I guess we need the average there, don't we?
That's right. We do need the average. Let's see. Can I copy these? Are they going to let me copy these? Okay. I'm going to try to paste them into Excel for you.
Okay, thank you.
Okay. I wasn't going to show you this step, but the more tricks you learn in Excel, the better of a scientist, more capable you'll be of analyzing your data, and really the better scientist you'll be. So I'm going to show you some tricks here. In this, and the way that you learn these tricks, and they'll be different by the time you get to your place and use your Excel, because Excel's always changing, right? But the way that you learn these things is you go to YouTube and ask, how do you do this in Excel, right? And there's lots of learning that can occur there. So you can't, but you need to have some foundation to start. So I'm going to show you a thing every once in a while. So here I have these values pasted in, but when I pasted them in, they just all went into one cell. So I can look at my data here, and I can go what we call text to columns. And then I open up a little wizard here where I can choose how I would like to separate it. I could do a fixed width, which works fine here. I could also do a delimited by, and then I choose the kind of thing I want to express the delimitation by. Either way, I end up getting those values like that. So now I'm going to take the average, equal sign average. Let's see, do I need to do anything else? It's from the population, and the population is already known to have a standard deviation of 5, right? So what else do I need to do?
Well, I think that's pretty much it. All we need there was the average. So you got 249, and you got 3 significant digits, so it's 250.
Very good. I can format this cell here to give me just no decimal places. There we go. So it'll round it for me. I can make sure I label this average.
Okay, now after you get your average, it's the average plus or minus.
Okay, so if I do plus or minus, whoops, maybe minus or plus, Let's see if I can, how I get the plus or minus sign. Insert symbols, symbols. There's my plus or minus sign. All right, so plus or minus 250, plus or minus, then what goes here?
That's the standard deviation 5 times, we want the 95%, right?
That's right, 95%.
It's 1.96.
Okay, so where did you get the 1.96?
Well, I got it right there. I kind of remember it, but you got it from the table up there, right? Yeah, there, right there, see?
All right, so there's confidence intervals for a normal distribution. Okay, very good. So, what did we say goes here?
5 times 1.96.
5, that's our standard deviation, times, where's my times value? 1.96. Okay, and then what?
Well, you get to divide it by because you have multiple values.
Whoops, I messed up there. What did I do there? 5 times 1.96. What are all those values in there? There we go. 5 times 1.96. Now what?
Divided by the square root of, you got 1, 2, 3, 4, 5, 6, 7.
That's right, divided by the square root of 7. So to get the square root of 7, I like to go like this. 7 to the raised to the, where's the raised to the 0.5 value? All right, excellent. So there it is. How do I have to, is that okay? 250 plus minus 3.704052?
Well, you don't need that many digits, and we're going to cut off at, the 0 is the last significant digit there, so we're going to cut off at 4, so it's plus or minus 4.
Very good. So this, we want 0, a number with 0 decimal places on it. So, very good. So, 250 plus or minus 4 should be our, we should be able to say, I'm 95% confident that there's a 95% probability, or we're 95% confident that the population's mean is between this distribution, which is 250 plus or minus 4. Okay, so we're 95% confident that our average is within that distribution. Okay, very good.